Hello, everyone, and welcome to this Factor This Power Engineering webinar, Cooling the Current Next Generation Thermal Management for HVDC Systems, presented by Advanced Cooling Technologies. I'm Kevin Clark, Senior Content Director of Factor This Power Engineering, and I'll be your host for today. Over the next hour, this technical webinar will explore how advances in cooling technology are enabling the next generation of high voltage direct current transmission systems. As power density rises, so does the challenge of managing heat, and traditional air and liquid cooling are reaching their limits. As power density increases, traditional air and liquid cooling are reaching their limits, introducing new challenges for reliability, performance, and long-term asset health. ACT's engineering team will introduce advanced two-phase cooling technologies, loop thermosyphon, and pumped two-phase cooling that are redefining what's possible in HVDC system design. You'll discover how these approaches are solving today's thermal bottlenecks, extending component life, and delivering the scalability needed for tomorrow's grid. Drawing from real-world experience, ACT experts will share practical insights into design considerations, integration strategies, and performance outcomes that demonstrate how utilities and OEMs can achieve higher power density with smaller equipment footprints. Before we get started, I'd like to go over a few housekeeping tidbits. The presentation is both live and interactive. You can ask a question at any time by typing it into the question box in the chat feature. You should use that for any technical difficulties you are experiencing as well. We recommend that you shut down any other applications you have open at this time so that you can fully concentrate on the discussion that you're about to hear and improve your machine's performance. This presentation will also be available on demand following this live event. A reminder email message will be sent to all registrants with a link to the archive once it is ready, and you will also be able to find it in the webcast section on the Factor This Power Engineering website. With that said, I'd like to now introduce our speakers for today. Knut Philipp is Director of Business Development for Industrial Products at Advanced Cooling Technologies. Mr. Philipp spearheads growth initiatives within the industrial market sectors. He joined ACT 2 years ago and brings a wealth of executive strategic leadership experience in corporate development, service engineering, and operations management to the ACT team. Matt Glessner is a product development engineer in vaporization and refrigeration group at Advanced Cooling Technologies. Mr. Glessner works on designing and building pump two-phase and loop thermosyphon products for a wide range of applications. You can see their full bios in the presenter tab. Without further ado, I'd like to turn it over to Knut Philipp for today's presentation.
Hey, good morning, and thank you for that introduction. And thank you, everybody, for joining this morning. We're going to spend a little bit of time here going through just a quick agenda overview. What we'll try to do today is just a quick introduction to who Advanced Cooling Technology is and who we are, how we operate. We'll go through HVDC and thermal challenges as an introduction, and then we'll focus heavily in this discussion about the thermal solutions that were just outlined briefly, followed by a Q&A. Before we get started with this, though, I'd like to run just a couple of questions of the group here. We'll just go through them one by one. The first one here is on a scale of 1 to 5, where 5 is very familiar. How would you rate your current knowledge of advanced cooling technologies, or ACT? 1, not at all familiar. 2, not very familiar. 3, vaguely familiar. 4, somewhat familiar. And 5, very familiar. If you can please acknowledge that within the window that you're seeing to respond, that would be appreciated. Again, the question is on a scale of 1 to 5, where 5 is very familiar. How would you rate your current knowledge of advanced cooling technologies? I'll give you just a couple of seconds here to complete that. All right, thank you. Seems like we have quite a few that may be new to advanced cooling technologies, and at the same time, some that are quite familiar with us already, but we'll go through a little bit of an overview just to level set everybody. For the next question, which topic interests you the most? First one is increasing power density. Second is reducing system footprint. Third would be improving reliability and or lifespan. And 4 is next generation cooling technologies. You can please respond to those as well. Again, the question is, which topic interests you the most? Give you just a few seconds to go through that as well. So then it seems very much so the next generation cooling technologies are of high interest, which is fantastic. That's what we'll be talking about here. And Matt will go into some great details from a technical perspective. And then the third question before we get fully going here, for those of you working directly in the HVDC space today, how much of your focus is on thermal management on a scale from 1 to 3, where 3 is it's your primary function? How would you rate your prioritization? 1 is not your area of responsibility. 2 is part of your broader group's responsibility. Or 3, again, it's the primary function, primary focus of what you do. Again, the question is, for those working in HVDC space today, how much of your focus is on thermal management directly? Okay, it seems like we have a fairly good mix of responses in all 3 categories, so we'll try to address that appropriately here. Again, at the end of this session, you will also be able to download these particular slides we'll be going through, and you can always reach out to us for further questions as they may arise. All right, very good. As we move forward here, I want to make sure that we get a quick overview of advanced cooling technologies. The company's been around since 2003. We are considered a relatively small company, under 500 employees, currently at 375. You can see here our manufacturing capabilities in the various locations. We are US based, headquartered in Lancaster, Pennsylvania, with additional facilities in York, Pennsylvania, and Anaheim, California. And our core values at the center of their innovation, teamwork, and customer care. We place a lot of emphasis on each of those for the reasons, very obvious reasons, especially on the innovation side, where we spend a lot of time and effort on research and development for next generation thermal management capabilities and technologies. So as far as certifications go, certainly ISO 9001, but also AS 9100D certified for aerospace production, because we do spend a lot of time, not just in the industrial sectors, but also in aerospace, military, defense, space applications specifically. So yes, our thermal solutions are currently in orbit around our planet. Giving you some more insights as to how we approach any of our thermal solutions. They are custom solutions specifically tailored to your individual needs. We understand the entire product program using a variety of different thermal tools, some that are off the shelf, many that are more proprietary, and then looking to operationalize the optimum solution for your system needs. And very importantly, not over designing that in the process. So some of the tools that are available to us, as I mentioned, you'll see some of them here that are considered off the shelf, but a lot of this is really the core competency of what our engineering team has in-house, and is able to develop these thermal solutions appropriate to your specific needs, all the way into system controls and validation as necessary. So this is just a quick overview of the overall technology portfolio, and without going into all of them in detail, you'll see a variety that are single phase, traditional liquid cooling, passive cooling, two-phase passive cooling, two-phase active cooling, very much so also on the energy recovery side, loop thermosyphons, environmental control units, and as I mentioned, also space applications. But we're here to focus today more on the energy side and power conversion systems. And a lot of those technologies apply directly within that space. As you can see, some of these examples here relative to active liquid and pumped two-phase cooling applications, loop thermosyphons, heat pipe assemblies, which we cover from a cryogenic all the way to extreme high temperature at the 1400 degrees C range. But importantly, in the bottom center, you'll see that it's ruggedized for any environment. So adverse environmental conditions, also from a shock and vibe perspective, but again, looking to optimize the thermal solution for your specific needs. So let's talk about HVDC and some of the thermal challenges that come along with this. The sector growth drivers are driven through efficiency, stability, and power density that you get out of the HVDC applications. Many of you know this already, but lower transmission losses on long distances, better submarine and underground cables. The asynchronous grid connections are a big part of this as well. lower infrastructure cost for long distances that leads into levelized cost of energy discussions. And then you have power flow control as well. But along with that, you get into some thermal challenges. And this is intended to outline this in some level of detail for you as to what we see and how our thermal challenges are addressed by our thermal solutions. So the higher heat flux, especially as you get into more compact environments, thyristors, IGBTs, et cetera, with higher power densities, but going all the way through, and I'm not going to read all this for you because, again, you can download this after the fact, but converter designs are a critical part of this. The cost per kilowatt is a consideration. I mentioned levelized cost of energy, or LCOE, is one of those drivers. Reliability of the system and durability and quality, which your end consumers will ultimately be the beneficiaries of, as will your product with these integrated technologies. Electrical isolation, a critical component of any power conversion system, but specifically in HVDC space. A lot of the technologies we'll be talking about today will touch on the intrinsic safety elements of using two-phase solutions and getting into some refrigerant-based systems. And last, but certainly not least, the lifetime cost of the system for the application itself, not just in terms of thermal management, but what it does for the other components within your solution to ensure long lifetime durability and reliability. So keep that in mind as you go along. On the left side, whatever the power or energy source is, in this particular example, it's a wind turbine. But as you go through that process from left to right, along the way, you have energy losses or thermal management requirements that are addressed through these technologies, whether they're friction losses or parasitic energy losses, or things that lead to reduced energy consumption and improved performance. These are the attributes of the technical solutions that we'll be covering here today. But again, waste heat is what the challenge really is for us. And whether it's generation, conversion, inversion, and transmission inefficiencies, all of these require advanced thermal management as we continue to evolve in power conversion and power distribution and transmission systems. And all of you out there that are working in this field directly need to focus, if you don't already, but I'm sure many of you do, need to focus on how to manage that waste heat load and balance that with the system level efficiencies that we're striving to achieve here. So fundamentally, what we're trying to get to are the benefits of thermal solutions that we promote here: low energy consumption, low maintenance requirements, low cost per kilowatt, the fact that they're scalable, and Matt will get into that in quite some detail, and then improved ROI and LCOE, the levelized cost of energy. Now, with that in mind, I'm going to hand it over to Matt, and he will take us through a number of solutions here.
Thank you, Knut, for that introduction. As Knut said, I'm going to dive a little deeper into some thermal management solutions for two-phase, look at a few case studies, and then we'll get into some Q&A. So as Knut alluded to here, one of the main challenges that we're seeing with HVDC and a lot of power electronics right now is increased thermal loads and higher heat fluxes. A lot of components like IGBTs, thyristors, high capacity bus bars, transformers, we're seeing higher and higher heat fluxes, and conventional cooling solutions such as air-cooled or single-phase pumped loops are not up to the challenge of cooling those. So just taking a look at some of those conventional approaches. First here being air cooling. This is, as many of you know, just an application where we use ambient or forced air. We're taking heat away from the electronics and ultimately rejecting it to that air. The advantages here is that it's usually very easy to implement, pretty simple setup, and if you have a low power situation or application, it can be very effective. The challenges here are the limitations. You're not going to get as much heat transfer coefficient, so especially when you have higher heat flux components, your air cooling is not going to be able to take away that amount of heat. Especially when you have those large power consumptions, you're going to need larger fans, larger blowers, and those are very high power consumption components. So you're not going to have nearly as great efficiency as you have with liquid solutions. So the other primary conventional cooling approach is a single phase cooling loop. So this will typically have deionized water or another water-based coolant circulating through a loop. It'll typically go through your power electronics, whether that's in a cold plate or immersion cooled, and be taking away heat from there and absorbing that, being pumped back to a heat exchanger. That heat exchanger, depending on the application, is often either a liquid to air heat exchanger, like a tube and fin heat exchanger, where you're rejecting that to ambient air, or oftentimes if you're a more seaborne application, you can reject that to seawater or another liquid loop. And then that fluid is pumped back into the heat producing components. So once again, this is in many cases, especially with lower power densities, you're going to have a lot of success with the single phase cooling loop. Limitations though, low isothermality. So what you're going to have is a lot of your power electronics are going to do more thermal cycling, which is going to reduce the lifespan of those components. Especially when you get into higher powers, you're going to need to be pumping your fluid a lot at greater flow rates as opposed to two-phase solutions, because that lower heat conductivity that requires a greater pump or greater fans, just a larger system footprint, larger power consumption. So you're not going to be as efficient there, and that cost per kilowatt, as Knut was talking about, is going to be much higher. So looking at two-phase cooling, the main reason two-phase cooling is such a powerful tool for us is this heat of vaporization. So we're storing energy into the latent heat of the working fluid, which is typically a dielectric refrigerant as opposed to water. We're making use of that boiling heat transfer, which is typically a lot greater and more efficient than typical convective heat transfer. So we're lowering the necessary temperature difference between your hot component and your working fluid. So you can operate these systems at where you have much higher ambient air, ambient fluid solution, as opposed to, and you can keep your electronics a lot cooler. So we're going to look at two main technologies here that we use. One is loop thermosyphon, which is a passive approach to two-phase cooling. And then the second is a pump two-phase cooling, which is an active solution. So just a kind of introduction into passive two-phase cooling. So many of you have probably heard of heat pipes. They're kind of the bedrock of passive two-phase cooling. They've been used for a long time and continue to be used. They typically consist of a copper tube that has a wick, which is a sort of fabric on the lining of that heat pipe. And then they have working fluid that, could be anything like water or ammonia or some more complex coolant. That working fluid will naturally travel to the heated end of the heat pipe, and it will heat up and vaporize, and then the vapor will travel to the far end of the heat pipe along the length of it. These heat pipes are great because you can have them at really long lengths and they're still going to operate as intended. As the vapor travels away from the heat source, it's going to recondense, get absorbed into the wick, and return to the heat source. So these heat pipes are great because they don't have to work with gravity, as you can see in that image to the right. As we get into thermosyphon and loop thermosyphon here, that kind of changes. So thermosyphon is basically a variation of a heat pipe. It does not contain that wick. but rather uses gravity to return that working fluid to the heat source. So a thermosyphon is dependent on the orientation of the system. It needs to have gravity to basically do its fluid movement in the so your condenser will always have to be above your evaporator. So that kind of leads into loop thermosyphon. So it's a similar technology to that traditional thermosyphon, but the main difference is that we're separating our liquid and our vapor flow. So in that normal thermosyphon, I can kind of see on the left, your vapor and your liquid are kind of in cross flow going right past each other as they're moving up and down the thermosyphon. In a loop thermosyphon, you actually are going to have a separate vapor line and a separate liquid line. So your liquid is going to travel from your condenser down to your evaporator and in one section, and your vapor is going to travel back up in a separate line. So that elimination of the cross flow eliminates some of those heat losses, and you're going to see much higher performance with the loop thermosyphon. So kind of a overview of loop thermosyphon. Like I said, it's relying on gravity. So the one major advantage here is there's no active pumping. So you're not having a mechanical component that could fail. You're not having the power consumption of that pump. Gravity is doing all the work for you. So when we're looking at a thermosyphon, a loop thermosyphon, we have four main components. We have an evaporator, a condenser, a liquid line, and a vapor line. So your evaporator, it can be many things, but oftentimes it'll be a cold plate, as you can see on the example on the right. In that left part, the inside view, essentially, here you'll have, depending on your application, that cold plate can be in many different orientations, or the internal geometries will change, but essentially you'll have your fluid moving through the cold plate, and it's going to be at saturation, or so you're going to have kind of a frothy, bubbly mixture, partially vapor, partially liquid, as it moves up the evaporator. And that's going to be taking away all that heat, rejecting all that heat. It's going to move up to a condenser that's located somewhere above it. In this example, the condenser is directly above it, but the one advantage of loop thermosyphon is your condenser, as long as it's vertically above your evaporator, it can kind of be located remotely, which is a great advantage. You necessarily have to have your whole system in the same area, which, in many applications, you have only a very small space claim for your thermal management. So that's your evaporator, your condenser. Depending on your ultimate heat sink, there's really two main heat exchangers we'll use. One will be a liquid to air heat exchanger, which is shown here. We'll typically use the tube and fin style, where we're blowing ambient air across it. That's going to cool that fluid back down, condense it, and it will return back. So then the last two parts there, the liquid and the vapor line. In this example, it's kind of shown here on the right. Our liquid and our vapor line are actually internal to the evaporator, which is, a great advantage. You have that flexibility in other applications, especially if the components are situated far away from each other. You can have long, either flexible hosing or copper tubing, or whatever it needs to be. But as long as your condenser is above your evaporator, those liquid and vapor lines are pretty flexible. So looking at some of the advantages we have over a single phase cooling solution, as we talked about, just in general, two phase, you have superior heat transfer efficiency, much higher boiling or latent heat. The no pump, you're going to have better, you're going to have passive fluid flow. So gravity is doing all the work. That's going to be much lower power consumption because you don't have a pump in there, and then greater reliability. You don't have to maintenance your pump. You don't have to service your pump. Can be very useful, especially in applications where your thermal management solution is not accessible, or you're in a situation where you don't have reliable power. Another thing, scalability and design flexibility. So I'll get a little more into scalability on the next slide, but in terms of your flexibility, as I talked about, really your evaporator is kind of where your heat generating components are. It's typically a cold plate, but your condenser can be located remotely. So you have a very small footprint where your heat generating components are, which is oftentimes very tightly packed, and there's not a lot of space claimed. So having that flexibility to move your condenser around, as long as you have that gravity, that height difference between the two, gives you a lot of options. And then dielectric fluids, when we're talking about high voltage components, it's very important to have that thermal, electrical isolation. So having dielectric fluids, which will typically use refrigerants, they're not conductive. You don't have to have an additional layer of non-conductive material between your components and the fluid like you would with water. And then lastly, that long distance heat transport, we can move the heat a long way away. So if you don't have easy access to, either ambient air or, your water loop or whatever it is that you need to reject your ultimate heat sink, you can move that heat a long way away to wherever that is. So getting back to that scalability, loop thermosyphon can be easily scaled. We've had loop thermosyphons that do 100 kilowatts of power dissipation. It really comes down to how you design the internal geometry of the evaporator, putting in the correct fluid charge, and calculating that pressure drop. One thing we've done at times is multiple loop thermosyphons, so we can use multiple line sets. So each of those is basically at a different saturation temperature, and so you can kind of step up your heat dissipation in multiple line sets, and you can get much greater heat transfer in that way and do a lot more power. So some things when we're looking at loop thermosyphon, one thing is you can use this in places of unreliable power. We had one situation, an application where they were essentially running on generator power a large percentage of their time. So loop thermosyphon was an ideal solution for that application because it uses such little power. You don't have a pump. We did run a fan in that situation, but it's much smaller powers, so much better efficiency. You're not throwing money away on that generator as much. But some design considerations, the orientation of your heat source and your heat sink. So like I've been saying, you need to have that height difference between your condenser and your evaporator. So when you're looking at if a loop thermosyphon is feasible, that's certainly the most important thing there. If you can get have your heat sink located above your evaporator. The passive approach doesn't allow active flow management. So with a pump solution, you can control that pump, make sure you're pumping the exact amount of, however many gallons per minute you want of that fluid. In a loop thermosyphon, that's not possible, but there are, when you look at the design, you're designing around how much fluid flow you want, and it's kind of set. What you can control and what we'll often control is we'll have temperature and pressure sensors, and that will control our fan speed. So we can still set evaporator temperature, set temperatures that we want to see at our junctions through our electrical components, and control the system that way. But you don't have that active flow management of the fluid itself. And then also compared to a single phase solution, you'll typically have an increase in costs of design or manufacture compared to those as upfront costs, just with the, oftentimes these brazed internal geometry evaporators can be a little more expensive than your standard cold plates. But the one advantage is you don't have nearly as much in terms of active cost, or running the system is going to cost you a lot less because there's a lot less maintenance and there's a lot less power draw. So next, I'm going to talk about pump two-phase cooling. So pump two-phase cooling operates very similar to a single-phase cooling loop. You'll have an evaporator, a condenser, a pump, and oftentimes you'll have a reservoir or an accumulator as well. That's not pictured in this one here, but that just like with loop thermosyphon, we're basically operating the system at saturation. So you have partially vapor, partially liquid running through your evaporator, and that's going to allow for a much greater heat transfer. So some of the advantages, one of the big ones that we see a lot of times is isothermal evaporators. Some of these IGBT, styrus, or some of these really high flux components are very finicky on how you need to keep those cool and at what temperature they need to be held at. So one advantage that pump two-phase has is since you're operating at saturation, your evaporator is very isothermal across it, a matter of sometimes a degree or two across an entire cold plate. So all your components are going to be kept at the same temperature. That's something that can be controlled and set, and there's a lot of control in that in the design. So if you say I need all these components to be held at 65C, you can design that in and set that, and they'll all be right at that, within a degree or so, compared to single phase where oftentimes you'll have a 10 degree, 15 degree delta across the cold plate. And so then that also leads into less power cycling of your components, longer lifespan for those electrical components. Also, you're going to see a lot lower flow rates and pumping power, which lets you have a much smaller pump. Also going to be less power consumption. We've seen probably about 80% reduction in pumping power needed. So on a system that you might need 10 gallons per minute for a single phase to meet your cooling demands, you might only need to pump 2 gallons per minute for the same cooling for two-phase. And so that's going to lead to a much smaller pump, less weight, less space claim, and less power consumption. So a lot of advantages there. Another great advantage is with high heat flux components working in a two-phase solution, you can isolate those components. We'll get into some internal evaporator designs, but you can isolate those components and meet those cooling. Oftentimes we'll see with anything over 100 watts per square centimeter, single phase cooling is not really able to achieve that cooling and keep them as cool as you need. Two-phase, we have had pump two-phase designs that have got up to even a kilowatt per centimeter squared. So there's a lot of advantages there and how much you can do with those high heat flux components. Kind of similar to loop thermosyphon with our dielectric fluids and our electrical isolation, makes that part of the system design a lot easier. You don't have to make sure that you're not conducting into your water or into your fluid and into your system with all the refrigerants we use are dielectric and compatible with HVDC systems. So taking a look at evaporator designs, like I was saying, one great thing at pump two-phase is we can really customize the evaporator. It really depends on the needs and what your electrical components will look like. So sometimes you have very simple cold plate designs to really complex geometries like the one you have on the right. That cold plate was built out of 3 different sections that were raised up. That bottom one is a manifold one, so you're putting all the fluid in there, and you can really isolate components, design fluid pass around hardware, make sure you have the right fluid flow under all your main high heat flux components. So there's a lot of design flexibility in those, and you can really tackle some challenging thermal solutions. And then kind of getting into control. So typically when we're controlling a pump two-phase system, we have a pump that can be modulated in how fast it's running, and the fans for the condensers if we're using a liquid to air heat exchanger. We'll use temperature sensors, pressure sensors, flow meters that are giving input back to a PLC, and we're controlling, and it will depend on what we're controlling. Oftentimes what customers want and what the application demands is we're really trying to control our evaporator temperatures, the junction temperatures to the electrical components. And so we can set points on the temperatures for there, and we're controlling oftentimes it will be the pressure actually of the fluid. Sometimes it'll be the temperature, and that way we can kind of control where what our saturation temperature is, and we're making sure we're keeping the evaporator and our junction temperatures below any requirements. And then the system will modulate the pump speed and the fan speeds to make sure that we're keeping those below those limits while not using any excess power to keep them extra cool. And then looking at scalability, pump two-phase is great for scaling to large systems. We have an application we're working on now that has 400 cold plates. So you can have one system feeding a large quantity of cold plates, large quantity of manifolds, and multiple different electrical systems. So it's, especially as you scale up, it can oftentimes be more advantageous cost-wise than having one small system for each individual electrical system. So you can have all your pumps and your fans and condensers all tied into the same control scheme, all your fluid running through the same system, and then broken out between all the different banks of electronics. So you can see on the bottom there just a picture of how we've done it before. Each of those little boxes that you can barely see there, that each of those has 5 cold plates in it. So this is our look at what 400 cold plates would do. This system is doing 45 kilowatts of power dissipation. And we're looking at doing some systems that are significantly more than that, but the advantage of pump two-phase, it can scale to that. You just need to increase the number of cold plates. Sometimes you need more pumps and condensers, but they can all run through the same system and all use the same loop of fluid. So some considerations when we're talking about pump two-phase. One of the main ones we see when we have customers that are looking for a pump two-phase solution is the isothermality. It can be very important for a lot of electrical components to keep that temperature difference across components very low. So in those type applications, pump two-phase is a great solution. Some of the potential drawbacks of pump two-phase is it does add complexity. You have compared to your loop thermosyphon, you add the pump. As opposed to your single phase solutions, you have to deal with refrigeration handling. You have much higher pressure in the system than a single phase loop, so there's some additional complexity there. The upfront cost is oftentimes higher due to that complexity. There's extra time in design, extra time making sure that your two-phase boiling, you're accounting for any flow instabilities. That can certainly be a challenge in design, but during operation, you should hopefully have, since you're running your pumps a lot slower, or you have much smaller pumps, you have less power consumption. You oftentimes will have less maintenance schedules on a pump two-phase loop as opposed to single phase. So even with the higher upfront costs, you'll oftentimes make that cost back during the operation of the system. So looking at working fluids, as we talked about, both loop thermosyphon and pump two-phase use refrigerants, which are dielectric. We're absorbing that heat during phase change, and they'll do that better than water. A lot of water mixtures that are used in single phase. Two main types of refrigerant we'll use are hydrofluorocarbons and then HFOs. So higher hydrofluorocarbons are probably a lot of the refrigerants you've heard of are R410, R134A. They're stable, dielectric, non-flammable. So they are staple in most refrigeration systems you'll see, especially historical ones. They're very, very useful. The one drawback is they have high global warming potential. So we're seeing more and more in some applications that is something that is a concern, and some industries are moving away from those. So HFOs, they have been a newer thing. They've been specially designed to have lower global warming potential, but they still have excellent heat transfer coefficients. The one drawback is some of those HFOs oftentimes are mildly flammable, and they also might have, depending on the one, they have some are only applicable in certain pressure ranges. So looking at HVDC, the dielectric is probably the biggest thing you guys are looking at, and an advantage, but you're looking at for that high voltage isolation, and you want to make sure you're considering temperature and pressure ratings. And if global warming potential is a factor in that choice, it's important to consider as well. So looking at just an overview, I won't go all the way into all these. This kind of summarizes some of the stuff I talked about. Just a trade study on single phase versus loop thermosyphon versus pump two phase. So your loop thermosyphon, you're reducing those mechanical components, higher reliability. You don't have that pumping power, but you are dependent on gravity. Loop thermosyphon pump two phase, you're going to be able to meet higher heat flux components, stuff much over 100 watts per centimeter squared, whereas pump single phase is going to have much harder time with that. Isothermality as well, that's another big advantage for the pump two phase and the loop thermosyphon. When we're looking at the complexity, pump single phase, is usually going to be only moderate mechanical complexity, much lower cost up front, but can be much higher cost long term, as loop thermosyphon especially is very low maintenance and very low power consumption. And then so for HVDC, in terms of low density applications, there's still a use for single phase solutions. They can serve those applications well, but when we're looking at higher densities, higher powers, your two phase solutions are going to offer things that single phase cannot. And then just putting some numbers that this is just showing pump two phase as opposed to air cooled and water loop. So I mean, see there, this is maybe hard to read, but if you look at third one down, that water cold plate, this is a pumped water loop at 6 gallons per minute. And it's doing less power than the the pump two-phase loop is doing at 1.2 gallons per minute. So only 20% of the pumping power and doing, almost 50% more capacity. So a pretty significant difference there. Next, I'm going to look at a few case studies here. I won't spend a ton of time on these just so we can get to some Q&A. First, looking at a pump two-phase solution we did for a wind turbine. So on this wind turbine, they had a pump loop that they were cooling gear oil. So the big gears that go into your wind turbine, they had the oil due to friction gets very, very hot. They had to cool that down and cycle it back to the gears. We designed a loop thermosyphon for them, dissipated 75 kilowatts, and it replaced that past the pump system. So that greatly reduced our maintenance costs, or their maintenance costs, which is, as you can imagine, maintenance up in a wind turbine is not inexpensive. And due to the height of the turbine, loop thermosyphon was a very useful technology because of the gravity. You have a lot of height difference to work with there. So as we talked about, no moving parts there, so less greater reliability, less maintenance, and then high thermal efficiency. So you can see this is our condenser coil on top of the wind turbine, and then it travels actually down to where it gets the heat to the gear shaft. So here's just some kind of testing we did when this was first implemented. Since we've implemented, I want to say thousands, but at least hundreds of these on the wind turbines. But we were looking at dissipating 75 kilowatts of heat from that gear oil. So we simulated the air going across that coil at ambient air, and we were testing the pressures and temperatures at 10 different locations along the loop here. And what we were really looking for is a temperature uniformity and a low temperature delta. So what we saw when we were testing this, we saw just a 6-degree gradient across the entire loop. So pretty good isothermality there through the system. And then only 8-degree temperature difference from the ambient air to that max temperature. So the one advantage we talked about with two phases, you can have a much tighter temperature band between your ambient air or your heat sink and your fluid temperature, or what you ultimately want your components or your oil or whatever it is to be. So great effectiveness on that one. And now just a quick example for a small HVDC application we use pump two-phase on. So this was a small next generation HVDC power module. It had two 150 watt silicon chips. The heat flux of those chips was only 52 watts per centimeter squared, but they were looking at implementing some chips that had 900 watts, so same footprint, so that would be 310 watts per centimeter squared, and they had to keep that maximum junction temperature down at 150 C. So first, selecting fluids. In this case, the customer needed a low global warming potential fluid, so we ended up choosing R1234YF. So it's significantly lower global warming potential. It's not quite as efficient as R134A, which we often use, and it does have mild flammability, but that was based on the requirements in the application. We had to choose that fluid. And then here's some analysis at 150 watts. So this is two chips there. And we gave a flow rate of just 0.25 liters per minute. and we kept the chip temperature down at 60 C, so far below the temperature requirements. And then for our analysis at 900 watts, the higher that 300 watts per centimeter squared watt density, the flow rate had to be increased up to 1.5 liters per minute, but you were able to keep that chip temperature below the limit there. You're at 124 C. That was the chip temperature, which I think kept that is what they're looking for in terms of operating temperature. And then just kind of a comparison to single phase, looking at the 150 watt, we were able to find a solution that 1 liter per minute for the 150 watt case. But you had to, so that was greater than the flow rate needed for two phase, and you had greater junction temperatures. And then when we moved to the 900 watt case, you were not able to find a solution at that case. So kind of where we talked about before, there's still places where single phase can be useful, but once you're really increasing those watt density, those power densities, those heat fluxes, greater than 100 watts per centimeter squared, oftentimes two-phase solutions are going to be one of your only options and going to save you a lot of problems. So I think that's everything I have. So we have almost 10 minutes to do Q&A.
That's right. Gentlemen, terrific presentation. Very much appreciate it. You've drummed up quite a bit of interest, and we've gotten quite a few questions in here, which we'll get to as many as we can in the last few minutes. I did want to note, as somebody did ask earlier, in case you were late, somebody did ask, is this being recorded? Will I have access to this presentation later? The answer is yes. This presentation will be archived on Factor This Power Engineering, and we'll be sending out a link following the presentation's completion. But let's get right to some of the questions that have come in. Let's start with this question to whoever would like to answer. Have you installed systems larger than 100 kilowatts thermal?
Yeah, I can take that one here. So the 100 kilowatt thermal is not a maximum. Certainly larger systems are deployed. They're fully scalable, as Matt outlined. The example on the fielded unit that we used for the wind turbine, those same applications wanted twice that application, depending on the type of wind turbine and the power or heat dissipation requirements of the application. Just to add to that, in that particular application, it's also truly free cooling, because it does happen to be in a wind turbine application where you've got a very large fan sitting at the front of the entire nacelle that only operates when there's motion, and therefore we have truly free cooling. But as Matt outlined, those applications can be scaled to any size. It comes down to a couple of points, one being the size of the condenser, whether or not you're using radiation or if you're using fans to make it more compact in terms of the space claim that you're talking about, or if there's a liquid to liquid heat exchanger that could be tied into it as well. But all those factors would be considered in terms of scalability for the application.
Terrific. Another question that came in about halfway through the presentation: what are the limitations of using these siphon systems?
Yeah, I can take that one. Really, it comes down to pressure drop and gravity head. So depending on your orientation, like I said, you have to have that condenser above your evaporator, and depending on what cooling you need and what flow rate you need, sometimes you need to have a greater height difference there than other situations. We've had ones that we've only needed to have, less than a foot between our evaporator and our condenser over, a 24-foot span between them horizontally. There's only 1 foot vertically. But sometimes there are limitations when it comes to that height difference. In terms of capacity, like Knut said, there's not really limitations in terms of overall capacity. You can design these systems for really large systems, where it really comes down to your available space for that condenser, and how much space claim you have to do the evaporator. So you need to design the internal channels of your evaporator to do that cooling. So in terms of kilowatts or total power capacity, there's really no limit. But in terms of orientation and space claim, you need certain situations that they can work in, and there's only but for the most part they can work in most situations.
We do appreciate all the questions coming in. We'll try. We know we won't be able to get to all of them, but we'll try and get to as many as we can. Here's one that came in about the terms that were used in the presentation. This person asks, sometimes you use the term cold plate and other times evaporator. Which is which, and where are they located?
Yeah, so I guess evaporator is probably the broader term. Evaporator will really comes down to where we're collecting the heat. So wherever your heat generating components are, sometimes we might have an evaporator it's collecting heat from ambient air from a server rack. But evaporator is really the term we're using where our fluid is coming in there, and then it's boiling, and it's at that saturation. So typically, oftentimes, a cold plate is what we'll use, especially if we're direct cooling for power electronics. So, like you have a circuit board with a bunch of power electronics on it, we'll design a cold plate that acts as the evaporator, and it'll have internal channels in it where your fluid flows, collects the heat from those power electronics, and then boils and vaporizes and moves on to your condenser. So sometimes in certain applications they're interchangeable. Evaporator, I would say, is the broader term, because sometimes evaporators are not cold plates, but most in a two-phase system, a cold plate will be an evaporator.
Another question that came in, how is system pressure managed in pump two-phase systems, and what safety mechanisms are typically integrated?
Yeah, so there's a lot of things we do. So we're typically in pump two-phase systems, we're dealing with much higher pressures, sometimes 300 psi or greater. So we will have pressure sensors in there that we're monitoring. They will alarm if we're seeing pressures greater than we want to see, or that it's designed for. And then typically we'll install a pressure relief valve that will has a set point on it. And so if your system's set at 250 psi, you might set your pressure relief valve at 300. So if you overpressurize the system, the pressure relief valve will release that pressure and keep the system working safely.
Gentlemen, perhaps this might be a bit rapid fire, but I always like to ask if you have any concluding thoughts for our webinar audience today. So for either of you or both of you who wants to take a crack at this with a minute to go, any concluding thoughts here?
Yeah, I'll just start off quickly. First of all, thanks everybody for joining today. The important message here is that for HVDC systems in particular, these technical solutions for thermal management apply directly. And we've seen quite a bit of uptake in terms of passive systems, meaning the loop thermosyphons, as well as active system interest relative to next generation applications. And this certainly leads to downstream opportunities. If you'd like to engage with us on any of these topics, please feel free to reach out. We'd certainly be able to entertain any of those discussions and questions, and even have an ad hoc meeting as necessary to ensure that we have a good understanding of your thermal challenges, and then we'll provide some guidance and input before we determine if there's a good fit to move forward with actual project work. But again, thank you for taking the time today to join us here.
Very much appreciate it. We are about out of time. I'd like to thank the Advanced Cooling Technologies team and thank you all for joining us today. Once again, the presentation will be archived and can be accessed on the Factor This Power Engineering website. You'll get a reminder email with that to all registrants with that direct link. You should also see a survey link appearing on the webinar chat. We would really appreciate the feedback there. Thank you all for joining us today, and we look